Okay, we can call the total force on the charge as Lorentz force. Okay, so what will be Lorentz force? You can simply take it as F. What will be that? F is a vector and it is electric Lorentz force plus magnetic Lorentz force. Right? Electric Lorentz force plus magnetic Lorentz force. That is total Lorentz force. We can write the magnitude of that. How we can write the magnitude of this? What is electric Lorentz force? QE. QE is electric Lorentz force plus what is magnetic Lorentz force? Yeah, Q into V cross B. Q into V cross B. That was magnetic Lorentz force. Q into V cross B. So F is equal to QE plus Q into V cross B. If you are writing it as vectors, how will be this equation? Electric field is vector, velocity is vector, magnetic field is vector. This will be the equation. Okay, and this is Q as a common term. You can take out Q. You can take Q as a common term. Then how will be the equation? F is equal to, if you are taking out Q, then Q into inside the bracket E plus what is this? V cross B. V cross B. V cross B. Don't write it now. V cross B. This is now the equation, and this equation is the equation for total force acting on the charge in both electric field and magnetic. Total force acting on a charge which is moving in both electric field and magnetic. Okay, that force is called Lorentz force. Total Lorentz force. That force is called total Lorentz force. Did you understand? You can write it. Jovita, Natasha, Sidra. Should I repeat it?
Yes, sir.
Should I repeat it? Is this okay? We are talking about the Lorentz force, and this is total Lorentz force. We have seen electric Lorentz force and magnetic Lorentz force. Electric Lorentz force is the force on the charge in an electric field, and magnetic Lorentz force is the force on a charge which is moving in a magnetic field. And the Lorentz force, or simply total Lorentz force, or simply Lorentz force is the force on a charge in both, moving charge in both electric and magnetic field. Okay, so that's Lorentz force. F is equal to Fe plus Fb, and this is Fe's equation. This is equation for Fb. That's it. Okay, write the heading. Then write force on a moving charge in both electric and magnetic field. Force on a moving charge. This is the heading. After the heading, you can write force on a Lorentz force. That's our heading. Force on a moving charge in both electric and magnetic field. In both electric and magnetic field. In both electric and magnetic field. Okay? Then you can write what is on the board. You can write what is on the board. What is this force called? This force is total Lorentz force or Lorentz force. Total Lorentz force or simply Lorentz force. You can write what is on the board. Okay? Completed. I just what did we discuss today? We discussed Lorentz force. What was Lorentz force? A moving charge in both electric and magnetic field. There will be forces acting on a moving charge if that charge is moving through an electric field and magnetic field. The total force on the charge is called the Lorentz force. And that will be Fe plus Fb. We have the equations for Fe and Fb. You can simply add them. And Q is a common term, so you can take out Q, and this will be the equation for total Lorentz force. Did you understand this one? Okay. Now we are going to see what is this magnetic field intensity. What is this P? Magnetic field intensity. We are new to this term, right? Magnetic field intensity B. We haven't understood what is that. What is B? Magnetic field intensity. We have to understand it more. Magnetic field intensity. Magnetic field intensity. Don't write it now. I will explain it after that. Magnetic field intensity. And magnetic field intensity can be represented with a letter B. And it is a vector. It is what? It is a vector. Okay. What is magnetic force? What is magnetic force? F is equal to Q into V cross B, or Q into VB sin theta, right? QVB sin theta. If sin theta is equal to 1, what is the equation for F? If sin theta is equal to 1, what is the equation for FB? QVB. That will be the equation for FB, right? I'm taking the maximum value of FB. I'm taking the maximum value of FB. Maximum value of FB will be QVB. This is F, magnetic Lorentz force. Isn't it? This is the magnetic Lorentz force. From this equation, I can write the equation for B. What is B? Yeah, F by QV. From this equation, I can define what is F, what is B. From this equation, I can define what is B. How's that? How is that? If I give the values for Q as 1 coulomb, V, that's velocity as 1 meter per second. Then what will be B? B will be M. Now you can define what is B. What is magnetic field intensity? Or there is another name for this, that's magnetic field strength. Now tell me, what is magnetic field intensity? It is the magnetic force and the conditions. Yeah. At the condition, it is the magnetic force when unit charge. No. Unit charge. This is velocity of the charge. Unit charge moving through magnetic field. Sorry. It is the force, magnetic force acting on a unit charge with the unit velocity. With the unit velocity moving perpendicular, right? Moving perpendicular to the field, or entering perpendicular, right? So that will be B. It is magnetic force itself. Magnetic force acting on a charge, magnetic force acting on a unit charge with the unit velocity. Isn't it? Isn't it? Magnetic force acting on a unit charge with a unit velocity, which is acting perpendicular. It is acting perpendicular. If it is acting perpendicular, theta will be 90 degree. If theta is 90 degree, sin 90 will be 1. That's why the equation is F is equal to QVB. Don't write it. Is it okay? Okay. So this is the definition for me. Tell me, what is the unit? What is the unit of magnetic field intensity? From the equation, you can find the unit. This is Newton divided by Coulomb. What is this? Meter per second. So what is this? What is this? Newton divided by, this is Coulomb, and this is what? Meter per second. What happens to the second? Yeah, second will be coming to the top. Second will be coming to the top. Then what is the equation? Newton second per Coulomb meter. Newton second per Coulomb meter. That will be the unit. If you see such type of unit anywhere, you have to understand this is the unit of magnetic field intensity. But we are using another unit for magnetic field intensity, that is Tesla. What's that? That is Tesla. Elon Musk company. Company of Elon Musk is no. Tesla cars, Tesla trucks, Cybertruck. So and Tesla is someone's name. It's derived from a name of a scientist. Was that Nikola Tesla? So you should give the capital T for the as the symbol. Capital T as the symbol. Okay, capital T as the symbol. Right? Okay. There is another unit also, Newton per ampere meter. Newton per ampere meter also. Newton per ampere meter also. So, if it is like this, what will be 1 Tesla? What will be 1 Tesla? How you can define 1 Tesla? 1 Tesla. 1 Tesla will be 1 Newton per ampere meter. 1 Newton per ampere meter will be 1 Tesla. 1 Newton per ampere meter will be 1 Tesla. How you can find Newton per ampere meter? How you will get Newton per ampere meter? Just like I said, Newton divided by what is Q? Q is Coulomb and V meter per second. Tell me where you will get this unit, Newton per ampere meter. Yes, Coulomb per second is the Coulomb per second is the what is Coulomb per second? Yeah, Coulomb per second is ampere. Coulomb per second is ampere. So Newton per ampere meter. That is Newton per ampere meter. Okay, so that's a unit of magnetic field. Magnetic field has 2 units, Newton per ampere meter or Tesla. You can represent Tesla with capital T. And 1 Tesla is equal to what? 1 Tesla is equal to 1 Newton per ampere meter. 1 Newton per ampere meter. That is 1 Tesla. So what will be 1 Tesla? How you can define it? That will be the force on force on a charge. If there is a current 1 ampere, if there is a current 1 ampere and it is moving to a length of 1 meter, don't have to do that. Okay, you can write magnetic field intensity P. Magnetic field intensity P. Then write this equation, F is equal to QBB. F is equal to QBB. F is equal to QBB. P is equal to F by QB. P is equal to F by QB. Then give Q is equal to 1 coulomb. V is equal to 1 meter per second. Then give Q is equal to 1 coulomb. V is equal to 1 meter per second. Then you will get P is equal to F. Right? Until that point. B is equal to F. B is equal to F. B is equal to F. Completed? Then you can write the definition for magnetic field intensity. You can write magnetic field intensity at any point. Simply write B. B at any point. Magnetic field intensity at any point. Magnetic field intensity at any point is the force experienced by unit positive charge. Is the force experienced by unit positive charge moving with the unit velocity perpendicular to the field. Moving with the unit velocity perpendicular to the field. Okay, you can write the unit of magnetic field intensity. That will be Tesla, capital T as the symbol for Tesla. Another unit is the Newton per ampere meter. Newton per ampere meter is another unit for Tesla. Okay, then 1 Tesla is equal to 1 Newton per ampere meter. You can write that also. 1 Tesla is equal to 1 Newton per ampere meter. We are going to define 1 Tesla. 1 Tesla is equal to 1 Newton per ampere meter. That is 1 Tesla. Put it in a box. 1 Tesla is equal to 1 Newton per ampere meter. 1 Newton per ampere meter. Okay? Did you understand that? Okay. Then we are going to study magnetic Lorentz force in detail. In this chapter, we will be studying about a magnetic Lorentz force or magnetic force. Okay? Let's see what is all about this magnetic Lorentz force. What we are discussing? Magnetic Lorentz force in detail. Magnetic Lorentz force in detail. What is that? Magnetic Lorentz force. What is the equation? What is the equation? Give me the equation. F B is equal to, I'm just simply writing F because there is no other force we are talking about, we are discussing about. There is only magnetic Lorentz. So F is equal to Q into V cross B. F is equal to Q into V cross B. And what will be the magnitude? This is the vector, force vector. And what is the magnitude? F is equal to Q V B sine theta. What is theta here? Theta will be angle between velocity and magnet. Did you understand that? There is velocity and magnet. As we understand, this is the magnitude. This is the magnitude of magnetic Lorentz force. What will be the direction? What will be the direction of magnetic Lorentz force? Don't write it. What will be the direction? You can find the direction using ideas. No. You can use two rules to find the direction of magnetic Lorentz force. Two rules to find magnetic Lorentz force. The first rule is we have to use two rules if there is a condition met. If there is a condition met. If theta is equal to 90 degree, you can use two rules. If theta is equal to 90 degree, you can use two rules. The first rule is Fleming's left hand rule. The first rule is Fleming's left hand rule. Fleming's left hand rule. I will write the second rule also, but we will be discussing Fleming's left hand rule only. That will be enough, I think. Okay. First rule is Fleming's left hand rule. Second one is right hand palm rule. Right hand palm rule. Right hand palm rule. Let's see what is Fleming's left hand rule. This is my left hand. Okay. Fleming's left hand rule is to find the direction of magnetic field. Direction of magnetic field. Okay. You can hold thumb, forefinger, and middle finger of your left hand in mutually perpendicular directions. In mutually perpendicular directions. Got it? And if this is what? If the forefinger is showing the direction of magnetic field, if the forefinger is showing the direction of magnetic field, and middle finger is showing the direction of velocity of the charge or current, velocity of charge or current, then thumb will show you the direction of force. Then thumb will show you the direction of force. In our time, we studied this with a very common term, like this: father, mother, child. Father, mother, child. Father force, mother magnetic field density. Child, that's current. That's current, right? That's Fleming's left hand rule for magnetic force acting on a current carrying conductor. We will discuss that further. Okay. Let's see what is Fleming's left hand rule. This is thumb, forefinger, and middle finger. I can only draw that like this. This is thumb, forefinger, and middle finger. And there is two fingers which is like this. So this is Fleming's left hand. Yeah, this is Fleming's left hand rule. What is this? This should be, yeah, this should be magnetic field. This should be the velocity. This should be the velocity of the charge or current. If it is positive charge. If it is positive charge, it will be velocity of charge. Okay. We are not talking about current here, just the charge. Okay. Now, this must be force. This must be force. Or you can simply draw like this. If this is B and this is V, they are mutually perpendicular to each other. They are mutually perpendicular to each other. Then magnetic Lorentz force will be in this direction. Okay? Perpendicular to both B and V. It should be perpendicular to both the B and V. Did you understand that? Okay, what is this right hand palm rule? This is our right hand. If you are stretching your palm just like this, the four fingers are showing the direction of magnetic field. Then thumb will be showing the direction of velocity. Then force will be perpendicular to your palm. Force will be acting perpendicular to your palm. That is right hand palm rule. I will just draw that right hand palm rule. That's very difficult to draw. Okay. This is the stretched palm. You have to imagine that. You have to use a little imagination. This is a stretched palm. Is that okay? This is stretched palm. And what is this? What is this? These fingers. These four fingers are showing the direction of magnetic field. And this is what thumb. Thumb is showing the direction of velocity. Then a line perpendicular to your palm will show you the direction of force. Direction of force. We just need this. Fleming's left hand. That will be easy to understand. Is that okay? Okay. Yeah. Yeah, same thing. This is another rule to find. Direction should be same. Okay. Direction should be same. You can use Fleming's left hand rule or right hand palm rule. Both will give you the same direction for magnetic force. Is that okay? Okay. Then there is one thing. If the magnetic field, if the magnetic field is acting into the paper, you can represent that with a cross. If the magnetic field is acting into the paper, you can represent that with a cross. If magnetic field is coming out of the paper, you can mark that with a dot. Now this is what? A cross. What is cross? Cross is magnetic field acting inwards. This is a convention. You have to remember that. This is a convention of direction. So you have to remember that. Magnetic field acting inward is this, and a dot is representing magnetic field acting outwards. So that's a point. You have to remember that point. Okay? You have to remember that. We can write a note. We can write it. Right? To find direction. If theta is equal to 90 degree, you can use Fleming's left hand rule or right hand palm. Right? Fleming's left hand rule or right hand palm rule. Only if the theta or angle is 90 degree. Only if the angle is 90 degree. Fleming's left hand rule. The second one, right hand palm rule. Second one is right hand palm rule. Okay? Can you draw that? Roughly draw the figures. If you draw the figure, you don't have to explain that in words. How you can explain this in words? If you hold thumb, forefinger, and the middle finger of your left hand in mutually perpendicular direction, and forefinger shows the direction of magnetic field, middle finger shows the direction of velocity of the charge, then the thumb will show you the direction of magnetic force. You don't have to write it. Just draw that. It will be equivalent to the writing. Don't have to write it. Just draw that and the right hand palm rule also. Roughly draw the figures. Roughly draw the figures. This is if theta is 90 degree. This is if theta is 90 degree. Only if theta is 90 degree. What is theta 90 degree means? What is theta?
Angle between.
What is theta? Angle between? Angle between? Magnetic field and velocity. Angle between magnetic field and velocity, that is theta. Theta is the angle between magnetic field and velocity. Roughly draw it. This is not important. Not important. That will be no problem. Yeah. And if you cannot draw, you cannot draw a figure for a left hand, you can draw this one. It will be equivalent to that. Yeah. Don't waste time on the drawing. Just roughly draw that. That's all. Right hand palm rule also. Right hand palm rule also. Completed? Right, this are say no. Right, this are say no.
Looks like I have to go. What is 6 fingers? 1, 2, 3, 4, 5.
Is it 6 fingers now?
What's a black finger? What is it?
Okay, you can write that note. Write a note. Magnetic field acting inwards. Magnetic field acting inwards into the plane, into the paper. Magnetic field acting inwards can represent that with a cross. With a cross. Magnetic field acting outwards can be represented with a dot.
So right hand palm rule is with this, right?
No. This is like this. Right hand palm. This is palm. Okay. That's the right hand thumb rule. Write that note. Magnetic field acting inwards can be represented with a cross, and magnetic field acting outwards can be represented with a dot. Put it in a box. Put it in a box. Okay? Did you understand that? Can I move to the next page? Write that note also. Magnetic field acting inwards represented with a cross, acting outwards will be represented with a dot. Study that. Understand that. We need that idea. Okay. Acting inwards and acting outwards. Cross and dot. Magnetic field acting inwards. That's it. Cross. Magnetic field acting outwards will be a dot. Got it? Okay. Then the next thing. If theta is not 90 degree, if theta is not 90 degree, if there is some angle between D and D, right? If theta is not 90 degree, if theta is not 90 degree, if theta is not 90 degree, then magnetic field and velocity vector will be acting at an angle theta. This is magnetic field and this is velocity of the charge. They are acting at an angle. They are acting at an angle theta. What is the angle between them? Theta. Theta is the angle between them. Theta is the angle between them. What will be the direction of the resultant vector? We have studied vectors, right? What is the direction of the resultant vector? No, not triangle. There is a right hand screw for that. Do you remember right hand screw rule? Right hand screw rule in 11th. Right hand screw.
That was screw.
Screw. Yeah.
So this right hand.
Do you remember that right hand screw rule?
It's like this one.
Yeah. No, there is a screw called a right hand screw. Right hand screw means if you are turning it in clockwise direction, that will be going into the plane. If you are turning it in anti-clockwise direction, that will be coming out of the plane. That's right. That is right hand screw. Okay. So if you have such an equation, and I want to recall your memory about vectors. If A is a vector and B is a vector, and A cross B is C. C is another vector. What will be the direction of C? What will be? Yeah, C will be perpendicular to both A and B. C will be perpendicular to both A and B. That is the result from cross product. That is the result from cross product. C will be perpendicular to both A and B. Like that, you are getting F. You are getting vector F from V cross E. So F will be, force will be perpendicular to both V and B. Did you understand that? It will be perpendicular to both V and B, or the force will be perpendicular to the plane containing V and B. If there is a plane and B is in that plane, V is in that plane, force will be perpendicular to both V and B. Like this. Right? Like this. That's all. Okay? So, if there is an angle between V and B, the force will be perpendicular to both V and B. Okay? And if we are measuring the angle in anti-clockwise, if we are measuring the angle in anti-clockwise, if we are measuring the angle in anti-clockwise, then the force will be acting outwards. Then the force will be acting outwards. Force will be acting outwards. The force direction will be like this. This is what? This is B cross B, not B cross B. They are different. You know that A cross B is not equal to B cross A. A cross B is equal to C. B cross A is not equal to C. It will be minus. Right? So I will draw that second figure also. This is what anti-clockwise. If it is anti-clockwise, the force will be acting outwards. Force will be perpendicular to both V and P, right? Perpendicular to both V and P, not only just perpendicular, acting outwards. Acting outwards also, perpendicular to both V and P and acting outwards. Acting outwards. Did you understand this first case? First case, simple. Second case is very simple. If you have B here, that's magnetic field, and the velocity vector here, that's velocity vector, and you are measuring the angle in clockwise. You are measuring the angle in clockwise. If you are measuring the angle in clockwise, according to right-hand screw rule, the resultant will be acting downwards. The resultant will be acting downwards. The resultant force will be acting downwards like this. Okay, so this is anti-clockwise. This is what? This is clockwise. This is clockwise. If you are measuring the angle in clockwise, if you are measuring the angle in clockwise, if you are measuring the angle in clockwise, then F is what? F is perpendicular to both V and D. Perpendicular to both V and D. Perpendicular to both V and D and acting inwards. And acting inwards. And acting inwards. Acting inwards. How can you represent acting outwards with a symbol? Acting outwards.
Oh my God.
Acting outwards will be a torque. Acting inwards will be a cross. Got it? So that's it. It's about the direction. You can write.
Because we, so you measure up from B to B, right?
Yeah.
So the first case is should go forward. If the V is down, then it's.
Yeah. If the B is down, then V cross B will be. If the it is like this, you are asking it like this, right? This is B and this is B. It's like this. This is what? This is clockwise B cross B.
Okay. Yeah, so we're supposed to take V cross B, right?
Yeah.
But
If you need B cross B, then that will be like this. Okay. Everything will be giving the same magnitude, but the direction will be changed. Everything will give you the same magnitude. Both this and this will give you the same magnitude. B cross B and B cross B will give you the same magnitude, but the direction of the magnetic force will be changed. Did you understand that? You can write. You can write. If an angle between B and V, if there is an angle between, if an angle between B and V, if an angle between B and V, if an angle between, if an angle between B and V, B and V, if an angle between B and V, the first case, you can draw that first case. You can draw that first case. Anti-clockwise direction. Angle is anti-clockwise direction. Angle is anti-clockwise direction. Angle is anti-clockwise direction. If angle is anti-clockwise direction, what happens? You can see that in both. If angle is anti-clockwise direction, then B cross B, F is perpendicular to both B and B, acting outwards. Acting outwards. Acting outwards. If the angle is anti-clockwise, then the resultant or force will be acting outwards. If it is clockwise, it will be acting inwards. It will be acting inwards. Right? What is on the board? Right? What is on the board? That's the first case. This is the second case. This is the second case. This is B cross B. That's B cross B. B cross B and B cross B. Okay. We have to add a node after this one. We have to add a node. You have completed it. Tell me, I'll give you that node. Completed? Abel? Topika? Okay. Now, let's see here. See here. This is force, right? And you have velocity here. What is the angle between velocity and force? Yeah, it's 90 degrees. Why? Force is perpendicular to both V and B, right? Force is perpendicular to both V and B. So the angle between force and velocity will be 90 degrees. And what is this velocity? This velocity is the velocity of the charge, or it is the direction of motion. It is the direction of motion. If force is perpendicular to the direction of motion, work done by that force is, I have studied that in 11. Like this. I will give you one example. A man is holding a weight and he is walking. A man is holding a weight on his head and he is walking. So his direction is towards right. The man is moving towards right. And he has a weight on his head. Right? Weight on his head. So there will be gravitational force acting on that weight. Gravitational force acting on that weight. What is the work done by gravitational force in this case? 0. Work done by gravitational force in this case will be 0. Why? The force is perpendicular to the displacement. Force is perpendicular to the direction of the motion. So the work done will be 0. Did you understand this? Okay. Now tell me, what will be the work done by magnetic force? It will be 0. It will be 0. Why is that? Force is perpendicular to the direction of motion. So work done by magnetic force is 0. You can write as a note. Work done by magnetic force is 0. 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 Why? Why it is 0? Force is perpendicular to the direction of motion. Reason. That's the reason. Force is perpendicular to the direction of motion. That is the reason. Force is perpendicular to the direction of motion. Force is perpendicular to the direction of motion. That is the reason. Force is perpendicular to the direction of motion. Did you understand this one? Huh? You got it? It is okay now. Can I move to the next one? Huh? Next, we have to discuss a derivation. We have to discuss a derivation. That is the force acting on a current carrying conductor in a magnetic field. Current carrying conductor in a magnetic field. If you have a magnetic field and you are taking a conductor and you are supplying a voltage to that conductor, and if you are bringing that conductor inside the magnetic field, there will be a force acting on that conductor. There will be a force acting on that conductor like this. If you have a magnetic field like this, there will be a magnetic field here, right? There will be a magnetic field here, not to south. There will be a magnetic field. If you are placing a conductor, imagine this is a conductor. If you are placing a conductor inside the magnetic field, what will happen? Nothing will happen because this is just a conductor. Nothing will happen. If you are connecting that conductor to a voltage, to a cell, what will happen? There will be current flow through that conductor. If there is a current flow through that conductor, there will be magnetic field around that conductor, and both these magnetic fields will interact with each other. Both these magnetic fields will interact with each other. Then there will be a force acting on that conductor. There will be a force acting on this conductor. Due to that force, the conductor will get deflected. The conductor will get deflected. It will be getting pulled or pushed according to the direction of magnetic field. According to the direction of magnetic field, we can use Fleming's left-hand rule to find the direction of force here also. Did you understand this one? If there is a current carrying conductor in a magnetic field, it will experience a force. We need to find the equation for that force. That's a simple derivation. We can see that simple derivation. I'll give you that simple derivation. What is that? What is our heading? What is our heading? Force on a conductor. Not just a conductor. Current carrying conductor. Force on a current carrying conductor. Conductor in an electric. In a magnetic field. Did you understand the heading? Force on a current carrying conductor in a magnet. Understood the heading? Okay. I will draw that case here. This is your conductor. I am elaborating. This is your conductor. Okay? And the length of the conductor is L. What is L? What is L? L is the length of the conductor. L is the length of the conductor. And I am giving you A. What is A? Area of cross section of the conductor. What is A? What is A? Area of cross section of conductor. Area of cross section of conductor. Area of cross section of the conductor. Now, I am connecting this conductor to a battery. I am connecting this conductor to a battery of voltage V, or EMF E. Okay. This is positive terminal, this is negative terminal. There will be current to flow through this conductor. There will be current flowing through this conductor. And now there is an electric field from positive to negative. Electrons will be moving opposite direction of electric fields. Electron will be moving in the opposite direction of electric field. So if the electric field is from positive to negative, what will be the direction of electrons? Electrons will be moving from negative to positive. Electrons will be moving from negative to positive. Electrons will be moving from negative to positive. Okay. Now there will be a motion of electrons inside the conductor. There will be a motion of electrons inside the conductor. Now we can derive the equation for that. We can derive the equation for that. We have equation for force. We have an equation for force, magnetic force. What is magnetic force? Force on a moving charge in a magnetic field. We have that equation. We have the equation for force on a moving charge in magnetic field. What is that equation? F is equal to Q into V cross B. That's our equation, right? That is our equation. But we are considering a current through that conductor. If there is a current through that conductor, we have to include that case also in this equation. We have to include that case also in that equation. The equation is what? The equation is F is equal to Q into V cross B. But who is Q here? Q here is the electrons. Q here is the electrons. Electrons passing through a conductor. What is Q here? Q here not just a positive unit positive charge, or it is not just positive charge. Q here is a collection of electrons, and that electrons are moving through the conductor. Did you understand that? Okay. We have to consider that case. How we can consider that case? How we can consider that case is very simple. We have to introduce the term N. Small n. Yeah. What is small n? N is number density or electron density. Number density or electron density. Do you remember what was N? Yeah, number of electrons per unit volume. What was that? N is equal to N by capital N by volume. Volume. There is velocity also, so I am giving volume. Volume. So N is equal to N by volume. And what is N? What is N? Capital N. Number of electrons. What is number of electrons? N into volume. That's N into volume. What is this? This is number of electrons. What is this? Number of electrons. That's number of electrons moving through this conductor. You got the number of electrons now. How you can find the total charge passing through the conductor? What will be the total charge passing through the conductor? Yeah, you can find the total charge passing through the conductor. How will be that? Q. Q is equal to N times E. What is N? Number of electrons. Okay. So what will be the equation? Is equal to, what is N now? N is N into volume. What is volume? What is volume? I can write volume here. What is volume? Yeah, volume is area into length. Volume is area into length. Volume is area into length. So I can use N. N is what? N into volume. N into volume. So N into small n into volume is area into length. Area into length into E. Area into length into E. This is what? That's charge. This is what? This is charge. Now you have a charge in terms of charge of electron, length of conductor, and the area of cross section of conductor, and all that. N also. N is number density. And you can use the equation now. What is the equation for force? Equation for magnetic force? Yeah, magnetic Lorentz force. Magnetic force. What is that equation? The equation is F is equal to Q into V cross B. V cross B. It is the equation, right? And we have the equation for Q now. So F is equal to, you can use that equation. What is that? N into A into L into E. Right? Okay. Now what is this? This is velocity of the charge. Do you remember any other term for the velocity of electrons in a conductor? VD, drift velocity. Do you remember that drift velocity? So V is, in this case, drift velocity. V is drift velocity in this case. So you can write drift velocity. You can write drift velocity instead of V into V. Now I am going to do something. Concentrate here. I am going to do something. I am modifying this equation. I am modifying this equation. What I am doing is, I am taking this VD, that's a vector. I am taking this VD out of the bracket and I am placing VD instead of L, in the place of L. And I am bringing this L inside of the bracket also, into the cross product. I am modifying this equation. As I said, cross product will only change the direction, not the magnitude. It will not change the magnitude, so I can do that. Right? It will not change the magnitude, so I can interchange the terms. That's so simple. Okay? The idea is simple. I am just interchanging the terms. If I am interchanging the terms, then what is this F? F is equal to, there is A, there is VD here, E is there, N is there. Okay? And inside the bracket, what is it? L is there, but L is now vector L. Because it is inside the bracket. It is the inside the bracket of cross product. So it will be vector L. Vector L cross B. Vector L cross B. Now we have, what is this term? What is this term? ABDEN. What is ABDEN? Yeah, ABDEN is I. Yeah. ABDEN is I. So F is equal to I. Is I a scalar or a vector? This is scalar. So I into, what is inside the bracket? L cross B. I into L cross B. This is the equation for force acting on a conductor in a magnetic field. Force acting on a conductor in magnetic field. Is that okay? And what is this? There is a new term here, L. There is a new term here, L. What is this L? L is a vector. It's a vector, but is length a vector? No. Length is not a vector. So this is what? L is a modified vector. We are taking L as a modified vector. Okay, L is a modified vector. And what is this L? L is a vector having the same direction and magnitude of current. L is a vector having same direction and magnitude of current. Okay, vector having same direction and magnitude of current, right? Vector having vector, it's a vector, just vector. What is the direction of that vector? Yeah, same as that of the current. Same as that of the current, not magnitude, same as that of the current. Not magnitude, just the direction. Direction will be same as that of the current. Magnitude will be the value of length. The value of length is length. So the value of length will be magnitude. And what is the direction? Direction will be direction of the current. So it's a vector now. What is a vector? What is a vector? Vector will have a magnitude and a direction. So it has a magnitude. What is the magnitude? Magnitude will be L. Magnitude will be L. Length to length. And direction.
Say this.
Yeah, same as that of the current. Direction will be same as that of the current. Direction will be same as current. Same as current. It will be same as current. Did you understand this? Okay. This is now F is equal to I into L cross B. What is L cross B? What is L cross B?
Force.
Yeah. L cross B is A cross B is AB sin theta. So L cross B is LB sin theta. LB sin theta. So F magnitude of force. Magnitude of force will be I into L into B into sin theta. ILB sin theta. Okay, I will write it like this. B I L sin. Will sin theta. To make it easy.
Yeah.
Easy to remember. This is what F is equal to L sin theta. B I L sin theta is the equation for force acting on a conductor in a magnet. Is that okay now? Okay. And this is what? Magnitude. B I L sin theta. How you will find the direction? Where you can find the direction of the magnetic field? Sorry, magnetic force. From which rule? Fleming's left hand. You can use Fleming's left hand rule to find the direction. Fleming's left hand rule to find the direction. Fleming's left hand rule to find the direction if the theta is 90 degrees. If the theta is 90 degrees. If the theta is not 90 degrees, you can use right hand rule. Okay? Did you understand this one? We can write this. We can write this. Start with the heading magnetic force. Force on a current carrying conductor in a magnetic field.
Do we know a figure on the top?
No, that figure is not necessary. This is just to understand it better. You can start from this one. You can write it as it is. Okay. Force on a current carrying conductor in a magnet. Draw the figure. The figure will help you to do this derivation. Figure will help you to do the derivation. That's L. L is length of the conductor. A is area of cross section of the conductor. And we are applying a voltage to the conductor also. Voltage to the conductor. Then what is N? Small n. Small n is number density or electron density. Number density or electron density. It will be capital N by volume. And the capital N will be small n into volume. That is number of electrons. That will be number of electrons. And what is volume? What is volume? Volume is area into length. Volume is area into length. Volume is area into length. So what is charge? Charge. This is actually total charge, right? Total charge. Total charge. You can write total charge. Instead of charge, you can write total charge. This is total charge. Total charge. So total charge is Q is equal to NE. Q is equal to NE. Q is equal to small NALE. That's your charge. Now you can write the equation for magnetic force. Magnetic force. What is the equation for magnetic force? F is equal to Q into V cross B. F is equal to Q into V cross B. F is equal to Q is NALE. Q is NALE. V is VD. Velocity is velocity of electrons. Average velocity of electrons. That is VD. So VD cross B. And F is AVDEN now. AVDEN in velocity. What is AVDEN? AVDEN is I, current. This current, I. Okay, what is L then? L is, and show the interchange also. Vector having magnitude of L. Vector having magnitude of L. Magnitude of length and direction same as current. Magnitude of length and direction same as current. So F is equal to I into L cross B. F is equal to I into L cross B. F is equal to I L B sin theta. You can write it as B I L sin. You can write it as B I L sin theta. If theta is equal to 90 degree, then you can use Fleming's left hand rule. If theta is equal to 90 degree, you can use Fleming's left hand rule. Otherwise, you can use right hand screw rule. If you use right hand screw rule, then force will be perpendicular to both the L and B. Plane containing L and B. So force will be perpendicular to both the L and B. Force is perpendicular to the plane containing or the plane of L and B. Force is perpendicular to both L and B. Perpendicular to both L and B. L and B. I am taking L as a vector. It is actually length, but I am taking it as a vector for our conveniences. F is perpendicular to both L and B. Actually, F is perpendicular to the plane containing L and B. Got it? Then we can discuss about two cases. Have you completed the derivation? Break. I will give you after the case. It will be the end of the derivation. Cases. End of the derivation. Completed. Then we have to discuss about the cases. Theta is equal to 0, theta is equal to 180, theta is equal to 90 degree, all that. Did you guys completed the derivation? Arfat, Jovita, Natasha, Sidra?
Completing, sir.
Completed. Okay. Where we will get the direction. The direction will be getting from Fleming's left hand rule or screw rule. Direction will be getting from Fleming's left hand rule or right hand screw rule. Can we discuss the cases now? Yeah. What do you have? No. Should be completed. This is based on resistance and also we have discussed this paper. Okay. 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 Then what is the force on a current carrying conductor in a magnetic field? F is equal to BIL sin theta, right? What is the first case? I am going to give you the first case. Case 1. In case 1, if theta is equal to 0, or theta is equal to 180, what will be the case of theta is equal to 0 and theta is equal to 180? Yes, sine 0 is what? Sine 0 is 0. What is sine 180? Yeah, sine 180 is also 0. Okay, so what will be the equation for magnetic force? What will be the equation of force on that conductor? Force on the conductor will be 0. Force on the conductor will be 0. Did you understand that? That is our first case. And what will be the case 2? Case 2. Yeah, case 2 will be theta is equal to 90 degree. If theta is equal to 90 degree, what will be sine 90? Sine 90 will be 1. Sine 90 will be 1. Then what is the equation for f? That will be BIL sine 90. Sine 90 is 1. Then BIL. Just BIL. That will be BIL is the maximum force. BIL is the maximum force because sine 90 is the maximum value of sine function. Sine 90 is the maximum value of sine function. So this is the maximum force on the conductor. Maximum force. It will be the maximum force. Got it? That's it. We can take a break. After the break, we will continue. We will continue at 5:53, 5:55, 5:55. We will continue at 5:55. Okay. No. Shivana is not here. Arfat, Jovita, Natasha, Sidra. Are you guys there? Arfat, Jovita, Natasha, Sidra.
Yes, sir. Yes.
Yeah, okay. Okay, then we have to discuss the next topic, that is moving charge in magnetic field, right? Charge is moving through a magnetic field and it is making first 0 degree, then 180 degree, then 90 degree, then in an angle. We have to take each cases. We have to discuss each case separately. Right? What are we going to discuss? Charge entering a magnetic field. Charge moving through a magnetic field. What happens to that charge? What will happen to that charge? How will be the motion of the charge? That's what we are going to discuss. Okay? So we are going to discuss about the motion of the charge. Motion of the charge in a magnetic field. In a magnetic field. We have several cases. Magnetic field. Okay. What is the first case? What is our first case? Charge entering the magnetic field at an angle theta is equal to 0 or theta is equal to 180 degree. What is theta is equal to 0 and theta is equal to 180? Theta is equal to 0 means parallel to the field. Theta is equal to 180 means anti-parallel to the field. Okay. So the first case is charge entering the field. Charge entering the field. Don't write it down. Charge entering the field. Charge entering the field parallel or anti-parallel to the magnetic field. Parallel or anti-parallel to the field. Anti-parallel to the field. To the field. Charge entering parallel or anti-parallel to the field. Let's see what is this case. What is parallel? What is parallel? Yeah, parallel means it is like this. If magnetic field is in this direction, now the charge is entering the magnetic field and the charge is also in the same direction. It's like this. This is the velocity. Motion of the charge, that's velocity. Okay, so what is the angle here? Angle here is 0. Angle between them is 0. If angle between them is 0, then what is sine 0? Sine 0 is 0. What is force acting on the charge? Yeah, force acting on the charge will be 0. So what will happen to this? What will happen to this charge? Tell me. What will happen to this charge if the charge is entering the magnetic field parallel to it? Nothing will happen. The charge will follow its path. Right? Nothing will happen. The charge will not deviate. The charge will move on without the deviation. Charge will move on without the deviation. Charge will not deviate. Charge will not deviate. No force on the charge. So charge will not deviate. Charge will not deviate. charge will not deviate. Did you understand this one? Okay. Let's discuss the case of anti-parallel entry. Anti-parallel entry. Now, the charge is entering the magnetic field with an angle. The magnetic field is acting in this direction towards the right. Now, the charge is entering opposite direction of the magnetic field. This is the direction of motion of the charge. Then what is the angle between them? What is the angle between them? Don't write it now. What is the angle between them? That's 180 degree. And angle between them is 180 degree. What is sine 180? Sine 180 is again 0. Then what will be the force? Force is 0. Force is 0. So what will happen? Charge will not deviate. Charge will not deviate. This is common for both the cases. Charge will not deviate in both the cases. Did you understand the first one?
Yes.
You can write it. You can write it. Charge entering the field parallel or anti-parallel to the field. That's our first case. Charge entering the field parallel or anti-parallel to the field. First, consider the case parallel to the field. First, consider the case parallel to the field. You can represent this figure. You can draw this figure. Theta is equal to 0, sine 0 is equal to 0, then f will be 0. Now, anti-parallel. Charge is entering the field anti-parallel to the field. Okay. So, theta is equal to 180 degree, sine 180 is 0, f is equal to 0. And this is the point. I will tell you the point to write. Charge will not deviate. The force on the charge will be 0. The magnetic force on the charge is 0. The magnetic force on the charge is 0, so charge will not deviate. Charge will not deviate. Charge will not deviate. You can write it as it is. You can write it as it is, no problem. Okay? Can we discuss the second case? Second one? No, this is the first case. Charge is entering the field parallel or anti-parallel to the field. Got it? Now we have to discuss the second case. Second case. What is the second case? Now the charge, you didn't write it. What is the second case? Yeah, in the second case, the charge is entering perpendicular to the field. That is the second case. Or 90 degree to the field. So what is second case? Charge is entering perpendicular to the field. Charge is entering perpendicular to the field. To the magnetic field. Charge is entering perpendicular to the magnetic field. What happens if the charge is entering perpendicular to the magnetic field? How will be that figure looking like? This is the charge. Charge is moving. This is the velocity. And the magnetic field is like how? Magnetic field perpendicular to this will be into the plane or out of the plane. Magnetic field perpendicular to this plane will be into the plane or out of the plane. Both will be okay. I am taking the magnetic field is into the plane. Magnetic field is into the plane. Right? Magnetic field is into the plane. Now, what is the angle between velocity and magnetic field? 90 degree. So, theta is equal to 90 degree. If theta is equal to 90 degree, what is sine 90? Sine 90 is 1. If sine 90 is 1, what is the value of magnetic force acting on that charge? Yeah. It will be Q V P. We are talking about a charge, not the current. Did you get it? We are talking about a charge. This is the velocity of the charge and magnetic field. So the equation will be F is equal to QV. Basically, they are the same equation, but we have modified that equation to get the equation for current in the case of current. Okay. Now the equation is what? Now the equation is F is equal to QBB. But we have to discuss some more if you are taking this. If you are taking this. What you can see here is there is a charge and that charge is entering the magnetic field. Right? Charge is entering the magnetic field. And there is a force acting on that magnet. What will be the direction of that force? What will be the direction of that force? That force will be perpendicular to the V and V, perpendicular to velocity and the magnetic field, right? So F, that's a force. Force is perpendicular to both V and B, right? V and B. V is what? Velocity. V is the motion, direction of motion, right? Direction of velocity will be the direction of motion. This will be the direction of motion towards the right. Direction of motion will be towards the right. What happens when force is perpendicular to the direction of motion? Or what happens when force is perpendicular to the velocity? We have studied that case in 11th grade. Let's recall your memory. This is what? This is circular motion. A particle is moving in a circular path. That is circular motion. If a particle is moving in a circular path, at this point, what will be the direction of velocity? Velocity will be tangential. Right? Velocity will be along the tangent at this point. So this will be like this. This is the direction of velocity. Okay? That will be the direction of velocity. Okay? And if we take another point here, what will be the direction of velocity at that point? At this point, the direction of velocity will be along the tangent like this. Direction of velocity will be along the tangent like this. Right? Both the cases, velocity will be along the tangent. Okay. Let's see. Let's draw the center point of the circular path. This is the center of the circular path. From the center of the circular path, I am drawing diameter here. I am drawing diameter. We know the angle between diameter and the tangent will be 90 degrees. Sorry. The angle between radius and the diameter will be 90 degrees. That's the radius, no diameter. The angle between radius and velocity, that's in the tangent. That will be 90 degrees. And do you remember about centripetal force? Do you remember about centripetal force? What was centripetal force? Yeah. The force which maintains the circular motion, that is centripetal force. Right? Centripetal force is the force required to move a particle along the circular path. That is centripetal force. Did you understand that? That is centripetal force. So, centripetal force is what? Force needed to move a particle along the circular path. And centripetal force will always be acting towards the center. Centripetal force always will be acting towards the center. Right? And what is the angle between centripetal force and velocity here? 90 degrees. What is the force and the velocity angle here? Force and velocity angle will be 90 degrees. So force is perpendicular to velocity is the condition for circular motion. Did you understand that? Force is perpendicular to velocity here. What is this? Force is perpendicular to velocity. What is velocity? Velocity is the direction of motion. Force is perpendicular to direction of motion. That is the condition for circular motion. That is the condition for circular motion. This is the condition for circular motion. So you can use that idea here. This is the condition for. This is the condition for. This is the condition for what? Yeah. This is the condition for circular motion. Circular motion. So the charge will attain a circular path. So the charge will attain a circular path. So the charge will attain a circular path. Charge will attain a circular path. Charge will attain a circular path. Did you understand this? Okay. Yes. We can write. Okay. Write the subheading. Charge entering perpendicular to magnetic field. Charge entering perpendicular to the magnetic field. That's our subheading. Charge entering perpendicular to the magnetic field. Sorry, Natasha, I will show you the slide after this note. Okay. Charge is entering perpendicular to the magnetic field. You can draw this figure. This is the direction of motion of the charge. This is magnetic field. The magnetic field is acting towards the paper. Inwards, it is acting inwards. Theta is equal to 90, sin 90 is 1, F is equal to QVB. Put it in a box. F is equal to QVB in a box. After that, you can write this down. Force is perpendicular to both velocity and magnetic. Force is perpendicular to both velocity and magnetic field. What is this velocity? Velocity means it is the direction of motion. Velocity will be in the direction of motion. So this is the condition for circular motion. This is the condition for circular motion, and you can show that condition on the right side of the notebook. You can show that condition on the right side of the notebook. So you can write, this is the condition for circular motion, and the charge will attain a circular path. Charge will attain a circular path. Charge will move in a circular path. Charge will attain a circular path with constant speed. The speed will be same. Speed will be same. We will see why. Circular path with constant speed. With the constant speed. With the constant speed. With constant speed. Completed? Have you shown the condition for circular motion on the right side of the notebook? Is it complete, Joseph? Evan? I know. I asked Joseph. What about you guys? Arafat, Jovita, Natasha, Sidra. Did you guys finish it? Okay. Okay, Sidra. Completed? You can write it. Natasha, tell me when you complete it. This is the previous slide, Natasha. Tell me when you complete it. Who will be providing the necessary centripetal force for this circular motion? Yeah. Which force will be providing the centripetal force for this circular motion? The magnetic force. So the magnetic force will be the centripetal force in this case. We have to derive some equations from that. Some equations from that part. Okay. Yeah, okay. Then what we are going to do? We are going to derive some equations for this circular motion. We are going to derive some equations for this circular motion. Who is providing the centripetal force for this circular motion? Magnetic force. Yes, magnetic force. Magnetic force is providing. Magnetic force is providing necessary centripetal force. The necessary centripetal force. Why the centripetal force is needed? Centripetal force for the rotational motion. Centripetal force for the rotational motion. For the rotational motion. Okay. And what is the equation for centripetal force? Centripetal force, or the letter for centripetal force is Fc. And Fc is now what? Fp. Fc is Fp now. Fc is what? Centripetal force. What is the equation for centripetal force? Do you remember the equation? Yeah.
So this is like no,
No. mv square by r. Do you remember that? mv square by r. That is the equation for centripetal force. M is the mass, v is the velocity of the particle, r is the radius of the circular path, and it is equal to fb. What is the equation for fb? QVB. Sin theta is 1. So QVB. What happens to this V? What happens to this V? V is the velocity. So it is cut and you will be left with 1V. MV by R is equal to QV. And you can find the equation for R. What will be the equation for R? You can bring this R to the other side, QV to the other side. This side. So there is already MV here. If you are bringing QV to the other side, then that will be MV divided by QV. MV divided by QV. What is this? MV divided by QV. What is this? This is my first equation. R is equal to MV by QV. What is R? Radius of the circular path. Radius of the circular path. This is the radius of the circular path. Radius of the circular path attained by that charge circular path. Okay. From this, we can understand an idea. What is that idea? That idea is this R is directly proportional to M.
and inversely proportional to
Yeah, inversely proportional to Q, and R is directly proportional to M means if the mass is increasing, the radius will be increasing. The mass is increasing, the radius will be increasing. And you can find the equation for V from this equation. What is the equation for V? Yeah, you can bring this the other terms to the other side. Then QB, V is QB R divided by M. V is what? V will be Q into B into R divided by M. QBR divided by M. QBR divided by M. Velocity is directly proportional to radius, isn't it? Velocity is directly proportional to radius. Yeah, velocity is directly proportional to radius. As the radius increases, velocity will be increasing. As the radius increases, velocity will be increasing. Velocity is inversely proportional.
and right the proportional.
Yeah, MV means M and V are inversely proportional. MV means M and V are inversely proportional. Do you remember AV? AV was a constant. Area into velocity was a constant. If area into velocity was a constant, then area is inversely proportional to velocity, or velocity is inversely proportional to area. Right? Like that. If you have something like this, MV, then M is inversely proportional. Okay, so this is what? This is velocity of the particle. Don't write it now. This is the velocity of the particle. This is the velocity of the particle. Got it? This is the velocity of the particle. Now, the third equation. For the third equation, I am bringing R to the other side. If I am bringing R to the other side, then that will be V by R. V by R is equal to QB by M. QB by M. What is this V by R? V by R. I'll tell you what is V by R. V is equal to R omega. Do you remember that? V is equal to R omega. What is that? Radius into angular velocity. That's linear velocity. Linear velocity is equal to radius into angular velocity. P is equal to r. Yeah, V is equal to r omega. Then what is V by r? Yeah, V by r will be omega. What is V by r? Omega. So this is omega. Omega is equal to QB by M. Omega is equal to QB divided by M. QB divided by M. This is what? Angular frequency. What is omega? Angular frequency. That's omega. That's omega. Angular frequency. Or gyroscopic frequency. Just another name, gyroscopic frequency, because there is no velocity term in it. That's right. There is no velocity term in it. Q, charge. T, magnetic field. M, mass. There is no dependence of velocity. Linear velocity is not depending on this angular velocity. Right? Right? Okay. So this is angular velocity, angular frequency or angular frequency omega. Angular frequency. Do you remember the relation between angular frequency and the time period? Right. Yeah. 1 by just 1 by t. What was the equation that is connecting? Yeah, omega is equal to 2 pi by t. Omega is equal to 2 pi by t, and t is equal to what was t? T is equal to 2 pi by omega. T is equal to 2 pi by omega. What is t? T is the time period. T is the time period. So time period can be written as time period. T is equal to 2 pi by omega. 2 pi by omega. By omega means you can multiply the reciprocal with 2 pi. By omega. 2 pi by omega means you can take the reciprocal and multiply here. If you are taking the reciprocal and multiplying it, what will be the equation? Reciprocal and multiply. 2 pi m by 2t. Did you understand that? Take reciprocal and multiply. That is 2 pi m by 2t. Now that's t. What is t? Time period. T is time period. Time period. T is time period. And the fifth equation. Fifth equation. We know the relation between frequency and time period. What is the relation between frequency and time period? Inversely proportional. Reciprocal of time period is frequency. So what will be the equation of frequency from this equation? Reciprocal of this very simple one. QB by 2 pi m. QB by 2 pi m. And from this equation, you will understand something. Both time period and frequency does not depend on velocity. There is no velocity. There is no velocity term here. So both the time period and frequency does not depend on velocity. These are the equations. 5 equations as well. Don't have to remember these equations. You don't have to study this equation by heart. But this only this equation or this idea will be enough.
So we use first one.
No, we may be using all the equations, but you don't have to study them by heart. Why? From this equation itself, you can find all the other equations. Don't reserve the space in the memory for this equation. Don't have to study this equation by heart. Just study this idea only. What is this? Fc is equal to Fb, or mv squared by r is equal to qb. From that idea, you can find all the 5 equations. Did you understand this?
Yeah.
Okay, you can write magnetic force is providing centripetal force. Magnetic force is providing centripetal force. This is the extension of circular motion. Circular motion itself. We are discussing on the circular motion. So this is the extension of circular motion. Magnetic force is providing centripetal force for the rotational motion. It will be enough. Magnetic force is providing centripetal force. Magnetic force is providing centripetal force. Magnetic force is providing centripetal force. Then Fc is equal to Fp. Fc is equal to Fp. V square by R is equal to QBV. V is cut from the equation. You will be getting 1V on the left hand side of the equation. So that will be MV by R is equal to QE. then R is equal to, can bring the R to the other side and QB to this side. So MV by QB. MV by QB is the R, radius of circular path. Radius of circular path. Then there is velocity. What is velocity? QBR by M. QBR divided by M. That's velocity of the particle. The velocity will be directly proportional to radius. Velocity will be directly proportional to radius. Okay. After that, third equation. You can bring this R to the other side. Then V by R is equal to QB by M. V by R is equal to QB by M. V is equal to R omega. V by R is equal to omega. You can substitute for V by R. V by R is equal to QB by M. In that equation also, you cannot find the term of velocity. This is independent of velocity. It is called gyro frequency. That's why we can call it as gyro frequency. Okay, gyro frequency. So it is angular frequency and it is called gyro frequency. You see gyro frequency somewhere, that is referring to this omega. That's angular frequency. Fourth equation. Omega is equal to 2 pi by t. T is equal to 2 pi by omega. So t, time period, is equal to 2 pi n by 2d. 2 pi n by 2d. And this is what? This is frequency. This is frequency. 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 After writing the equation of frequency, we have to write some points. Write a point after the frequency equation. If you have finished the frequency equation, I will give you that one. Got it? These equations are okay, right? Isn't it? 1, 2, 3, 4, 5. 5 equations total. Total 5 equations. You don't have to study them by heart. As a note, you can write at the bottom of these equations. For time period and frequency. For time period and frequency. For time period and frequency. There is no velocity term in the equation. For time period and frequency. For time period and frequency. There is no velocity term in the equation. There is no velocity term in the equation. There is no velocity term in the equation. Okay? There is no velocity term in the equation. They are independent of velocity. Got it? They are independent of velocity. They are independent of velocity. Okay? Can we discuss the next thing? Next topic? Huh?
Yeah.
The third one. The third case. What was the first case? Charge entering parallel or anti-parallel. What was the second case? Charge entering perpendicular to the magnetic field. Now the third case. Charge is entering the magnetic field with an angle theta. Charge is entering the magnetic field with an angle theta. Let's discuss that. Charge is entering the magnetic field at an angle theta. Charge is entering the magnetic field. So previous slide. Charge is entering the magnetic field with an angle theta. Charge is entering the magnetic field with an angle theta. Charge is entering the magnetic field at an angle theta. With an angle, at an angle theta. Okay. This is very interesting. Let me tell you what will happen here. Okay, what will happen here? Everything is interesting if you put your interest in it. Now there is magnetic field in this direction. This is what? Magnetic field. Magnetic field is acting in the right direction. Magnetic field is acting in the right direction. Okay. And charge is entering the magnetic field with an angle theta. Charge is entering the magnetic field with an angle theta. I am showing that like this. This is velocity now. Now velocity and the magnetic field is having an angle theta between them. Velocity and magnetic field is having an angle theta between them. Okay. The velocity is an inclined velocity. It is acting at an angle. Right? This velocity is now acting at an angle. So you can make two components of that velocity. You can find two components of that velocity. One component of the velocity will be here, acting in this direction. One component of the velocity will be acting in this direction. And the second component of the velocity will be here and it will be acting in this direction. So there will be two components of the velocity. There will be two components to velocity. One component will be acting parallel to magnetic field. Okay. The other component will be acting perpendicular to the magnetic field. What is the component of velocity that is adjacent to theta? Adjacent to theta. Yeah, cos theta or v cos theta. V cos theta is the component of velocity acting parallel to magnetic field. What is component of velocity acting away from theta? V sin theta. So the component of velocity acting perpendicular to the magnetic field will be V sin theta. Okay, so two components are there. First component is V cos theta. And what is this V cos theta? V cos theta in the same direction as that of the magnetic field. Same direction as that of the magnetic field. There will not be any force in that direction. There will not be any force acting on that component, velocity component in that direction. So it will be a constant speed. It will be getting a constant speed forward. There will be a forward motion because there is a component of velocity in forward direction. So there will be a forward motion. Did you understand that? There will be a translational motion because there is a velocity in that direction, a velocity in the direction of displacement. So the charge will have a displacement in the direction of velocity. Did you understand that? So the charge will have a displacement in this direction. Did you understand that? Charge will have a displacement in this direction. Is that okay? And what happens if the velocity and the magnetic field are perpendicular to each other? If the charge is entering the magnetic field perpendicular to the field, what happens? It will cause rotational motion. We have studied that in the previous case. It will cause the rotational motion. It will cause the rotational motion. If theta between velocity and magnetic field is 90 degrees, it will cause rotational motion also. So there will be a rotational motion also here. There will be a rotational motion along with a translational motion. What is the type of rotational motion? Rotational motion will be like this. So the charge will have a rotational motion like this. Can you see that? Charge will have a rotational motion perpendicular to the plane of magnetic field like this, and the charge will have a displacement like this. So what will be the direction or the shape of path of the motion? It will be a helix. It will be a helix. The charge will be rotating like this and it is moving forward. Right? Charge will be rotating like this and it is moving forward like this. Did you understand that? So the charge will attain a helical path. It will attain a helical path. Charge will move in a helical path. Its motion will be a helical motion. Not rotational motion, not translational motion, but a resultant of both of them. Combination of both the translational motion and rotational motion. Combination of both the translational motion and rotational motion will be a helical motion. Did you understand that? I can draw that helical motion like this. This is the helical motion. If this is the charge, If this is the charge will move in a helical path, and charge will have a displacement also in this direction. Charge will have a displacement also in this direction. Okay, charge will have a displacement. Okay. Then there is a term called pitch. There is a term called pitch. And you can represent pitch with the P. You can represent pitch with the P. What is pitch? Pitch is the distance traveled by the charged particle in the direction of magnetic field during one rotation. During one rotation, this is one rotation, right? This is one rotation, but there is not only rotational motion, there is translational motion also. So the charge is moving forward. Okay, so the distance traveled by the charge in the direction of displacement in one rotation, during one rotation. That is called the pitch. That is called the pitch. How you can find pitch? How you can find pitch? Pitch is a direction, sorry, distance. Pitch is a distance. How you can find distance if you have velocity? Velocity and time. If you have velocity and time, what is the distance? This is velocity. Velocity is equal to distance or displacement divided by time. What is displacement? Velocity into time. If you have velocity and time, the distance or displacement will be velocity into time. What is the velocity causing forward direction? What is the velocity causing forward motion? Which velocity is causing forward motion? V cos theta. So the equation is velocity into time. Which is the time we are talking about here?
Time taken for one.
Time taken for one rotation. It has a name. What is it? Time taken for one rotation has a name. What is it? Time period. That is time period. Time taken for one rotation is time period. Right? So velocity into time period. Velocity into time period, which is equal to what is the velocity causing forward motion? V cos theta. V cos theta is the velocity causing forward motion. V cos theta. What is the equation for time period?
1 by
2 pi m by qb. 2 pi m by qb. So V cos theta 2 pi m by qb will be the equation for pitch. Don't have to study that by heart. Just the idea only. You will get that equation from it. Just understand it. You will get the equations. Did you catch that idea? Understand it. Understand what it is talking about. You will get the equation automatically. Okay? We can write it. Third case. Charge is entering the magnetic field at an angle theta. Charge is entering the magnetic field at an angle theta. At an angle theta. You can draw this figure. You can draw that figure. Draw that figure. Draw the figure. The figure is very simple, right? It's the resolution of velocity. Resolution of the velocity vector. Completed the figure? Then you can write a note. I will tell you the dictate it. Just the figure. Then give a number 1. This one only. Okay? The resolution of velocity only. You can write velocity has two components. 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 First one, V cos theta. V cos theta. First one, V cos theta. V cos theta is parallel to magnetic field. V cos theta is parallel to magnetic field. V cos theta is parallel to magnetic field. Write it. V cos theta is parallel to magnetic field. Write it. Okay. Particle moves with a constant velocity along P. Below that, particle moves with a constant velocity along P. Particle moves with a constant velocity along P. Particle moves with the, what happens to the particle? Particle moves with the constant velocity. Constant velocity. Particle moves with the constant velocity along P. This is a translational motion. It's a translational motion, right? The second one, V sine theta is perpendicular to P. 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 Okay? You can write below that. Particle moves in a circular path. Particle moves in a circular path. Particle moves in a circular path. Second case. Particle moves in a circular path. Okay? The final point. The resultant of these two motions, the resultant of these two motions, the resultant of these two motions, that's the final point. The resultant of these two motions will cause a helical motion. The resultant of these two motions will cause a helical motion. The resultant of these two motions will cause a helical motion. Will cause a helical motion. You can draw that figure. You can draw that figure. You can draw the figure. The charge is in a helical path right now. Draw the helical path. Draw the helical path. And show the pitch also. Show the pitch also. We have to write what is pitch after that. Show that helical path. Have you written the helical path? What is the equation for radius? Radius of the circular path. What is the equation for radius of the circular path? Radius of the circular path. MV by QD. That is the equation. MV by QD. In this case, what will be that? In this case, what will be that? MV by QD. M will be M. V will be what? Who is responsible for rotational motion? V sine theta. For rotational motion, the cause is sine theta. So that is what? M V sine theta divided by QB. This is MV by QB now. If you need the radius of helical path, it will be like this. R is equal to MV sine theta by QB. You have to study this by heart? No. No. Just the idea only. R is what? R is what? R is MV by QB from that equation. R is MV by QB from that equation. And here V is the component of velocity which is causing rotational motion. Which component of velocity is causing rotational motion? V sine theta. So the equation will be R is equal to MV sine theta by QB. Got it? Okay. Then you can write about pitch. You can write about pitch. Right? Pitch. Have you shown pitch in that figure? Yeah. Then you can write pitch. Yeah, no. What the formula? We have to write what is pitch. Pitch. Pitch in bracket capital P. Pitch in bracket P. You can write what is P. Distance moved in the direction of magnetic field. Distance moved in the direction of magnetic field. Distance moved in the direction of magnetic field during one rotation. Distance moved in the direction of magnetic field during one rotation. During one rotation. Distance moved. Yeah, distance moved in the direction of magnetic field during one rotation. There is slight problem. What is this? Yeah, V is no, it's okay, right? V is equal to V cos theta and V is equal to 2 pi by 2 pi n by 2. Yeah, so R is equal to mv sin theta by qb is the radius of the circular path. You can show that equation with the along with that figure, along with the figure for the helix. And what is pitch? Pitch is P, and we wrote what is pitch. And now the equation, what is P? P is equal to, that's a distance, so velocity into time. It's a distance. Pitch is a distance. So it is velocity into time. Velocity into time. Which is the velocity causing the forward motion? V cos theta. So V cos theta into time period. What is time period? 2 pi m by 2b. That's the time. Okay? Completed? What about the others? Arfat, Jovita, Natasha, Sidra. Did you guys complete it? Did you take the notes?
The completing.
Okay. Okay, Jovita. What about others? Everyone? Are you finished? Can I move to the next one? Yeah, okay. Tell me when you complete it. After this, we have discussed about the application of moment of charge in both electric field and magnetic field. If there is an electric field and magnetic field and the charge is moving along through that magnetic and electric field, and we can use that idea to do some applications, to have some applications. There was two applications. Both of them are deleted portions. Both of them are actually deleted portions. But I will briefly discuss velocity selector only. For my satisfaction. Only. What about your school? Did they teach you velocity selector in the school? Do you remember that? Or do you have the? Did you study velocity selector as an application of this moving charge in both electric field and magnetic field? It's actually a deleted portion, but most of the schools are teaching that thing, that application. Do you have that?
No.
Is that your school note?
School not a PDF, not here.
Yeah.
Having a video.
There will be velocity selector if it is a PDF. If it is a PDF note.
Instead of notes, she's saying.
Is there any velocity selector after the moving charge in both the magnetic field and electric field? Biosavart law directly. No velocity selector. I will briefly discuss about this velocity selector. It's very easy to understand. And the discussion will give you some ideas how to do the numericals also. That's why I selected velocity. There is one more topic, cyclotron, and it is deleted portion. Cyclotron and velocity selector both are deleted portions, but I'm going to discuss velocity selector anyway. And this is what. Are you finished, Natasha? Can I move to the next page?
Yes, sir.
Okay. Let's see applications of movement of charge. Applications of movement of charge in both electric field and magnetic. Only one application is there, and it is very easy to understand also. That's called velocity selector. Velocity selector. Velocity selector. This idea is for the selection of a particle having a particular velocity. Why we are using this velocity selector? To select a charge. To select a charge having a particular velocity. What is the use of velocity selector? What is the use of velocity selector? Don't write it now. To select a charge, with a particular velocity, with a particular velocity. You get it? To select a charge with a particular velocity. Let's imagine there is so many charges, a bunch of charges, a beam of charges which is moving in a direction. If you have an electric field and magnetic field, using that electric field and magnetic field, you can particularly select a charge from that collection of charges, and that will be having a desired velocity. It will be having a desired velocity. We can select charges having particular velocities from a beam of charges. Do you understand that?
Yes.
Okay. It is like this. You have a magnetic field and electric field which is perpendicular to both of them, which is perpendicular to each other. Magnetic field and electric field are perpendicular to each other. Let's imagine that there is magnetic field and electric field are perpendicular to each other. If this is magnetic field is acting along y-axis or z-axis. You can take it as easy. And this is what? This is electric field. No, this is electric field now. There is electric field, and electric field and magnetic field is acting in perpendicular to each other now. And charge is entering perpendicular to both of them. Charge is entering perpendicular to both of them. So the velocity of the charge will be along the x-axis. What is this axis? This axis is x. This is y. This is z. Did you understand that? Then can you write the equation for EBP? What will be the equation of B? What will be the equation of B? What will be B? B is the velocity. Velocity is acting in x-axis. So you can write velocity as V I cap along the x-axis. Along the x-axis. And what will be E? Electric field. Yeah, E is the magnitude and J. Yeah. E J cap. What will be B? Vector B will be B into K cap. B into K cap. These are the values of V, E, and B. Let's find electric Lorentz force, Fe. What is electric Lorentz force? Q into E. What is E? Q into EJ. EJ cap. EJ cap. That is Fe. Got it? It is acting along y-axis. Can you understand that? Huh? Did you understand it? It is acting along y-axis. Why it is acting along y-axis? Because of the unit vector j cap. There is a unit vector j cap. That's why you can say that it is acting along the y-axis. So this is Fe now. Got it? That's Fe. Let's write second equation. Magnetic Lorentz force. What is the equation for magnetic Lorentz force? Yeah. Q into V cross B. Q into V cross B. Right? And Q into what is V? VI. Cross. What is B? BK. What will be this? Q into V and B are now magnitudes. You can take it out. V and B are now magnitudes. V and B are magnitude. Inside the bracket, there is I cap cross K cap. What is I cross K? I cross K. It is like this. I J K. If it is clockwise, then you will get the next unit vector. I cross J will give you K. K cross I will give you J. Okay, I cross K is in opposite direction, in anti-clockwise direction. If you are taking it anti-clockwise, then I cross K will give you minus J. Will give you minus J. So this is minus J. I cross K is minus J. Q V B minus J cap. You got it? Minus J cap. Look at FE and FB. FB is acting along minus J cap. What is that direction? Minus J cap. Downwards. Minus J cap is opposite direction of positive y axis. So it is the negative y axis. FB is acting along negative y axis now. FB is acting along negative y axis now. They are equal and opposite. Let's take FE is magnitude y equal to FB. What will happen? What will happen? FE is equal to FB. If their magnitudes are equal, then QE will be equal to QVB. If the magnitudes are equal, if magnetic force and electric force are equal, then what will happen? This Q will be cut. And what is velocity? Velocity will be E by B. Velocity will be E by B. So for a charge having this velocity, what will happen to that charge? For a charge having this velocity, what will happen to that charge? So if there is a velocity, if there is a charge coming in this direction, and its velocity is E by B, what will happen to that charge? Like this, like this, like this, like this. If you have a beam of charges like this, V1, V2, V3, many charges. You have many charges, and the charges are entering electric field and magnet. The charges are entering into an electric field, and a magnetic field. Charge is entering into an electric field. Yeah? It will deviate. Electric field and magnet. What will happen to the charges? 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 The charge V1, it is a charge having a velocity. It is entering an electric field and magnetic field. What will happen to it? There will be a force acting on it. There will be a force acting on it. Due to that force, it will deviate. It will deviate. And what will happen to V2? It will deviate. It will deviate. What will happen to V? V has the magnitude E by B. If it has magnitude E by B, then FE is equal to FB. Then FE is equal to FB. The force on the electric force and magnetic force on them, on that charge, is cancelling each other. So the force on that charge is 0. If the force on that charge is 0, nothing will happen. And you can catch that charge. You can catch that charge. You can select that charge. This is velocity selector. This is velocity selector. For V3 will be deviation. Okay? You don't have to study this velocity selector as a part of syllabus, but this type of questions can be coming. And this can be asked if they need it, if they want it. Why? It is not about velocity selector, it is just simply, you can use the simple concept there and you can find the answer. That's why. Is that okay? Okay, we can write it. Write velocity selector. It's about 7, right?
Yeah.
Can you take this note? Huh? Velocity selector. To select a charge with a particular velocity. So to select a charge with a particular velocity. To select a charge with a particular velocity. Let electric field and magnetic field are acting perpendicular. Let electric field and magnetic field are acting perpendicular. Let electric field and magnetic field are acting perpendicular. Right? Q is entering perpendicular to both. Q is entering perpendicular to both. Let electric fielder and magnetic fielder are acting perpendicular. Let electric fielder and magnetic fielder are acting perpendicular. Q is entering perpendicular to both. Q is entering perpendicular to both. After that, you can write what is on the board. After that, you can write what is on the board. You can take the note on the board. Electric Lorentz force and magnetic Lorentz force. FE and FB are opposite. Let FE is equal to FB. E and FB are opposite. Let FE is equal to FB. Then QE is equal to QEB. V is equal to E by B. Write that up to that point. V is equal to E by B. V is equal to E by B. V is equal to E by B. Right up to that point. After that, you can write this force on charge having velocity is equal to E by B. Velocity E by B. Velocity E by B, comma, F is equal to 0. That's the point. Force on charge having velocity E by B, F is equal to 0. That force is equal to 0. E by B, comma, F is equal to 0. That force is equal to 0. They travel without deviation. They travel without deviation. All right. They travel without deviation. They travel without deviation. They travel without deviation. Such charges can be selected out. Such charges can be selected. Such charges can be selected. Huh? After that, you can throw this diagram. No. We have completed that. It will be our session for today. After that, we have to discuss about the bio-observatory. What about tomorrow? Can you come tomorrow? We have maths. What about the others? We have maths. Kopika? You are there. When your maths class will be over? You will be here, right? Abhay? No, you will not be here. I know that. And when will your maths class will be over? 8. I will make some other arrangements, most probably in Tuesday. Do you have a Tuesday? Do you have any session for Tuesday? You have a practice.
No.
What's practice?
I go for rugby.
Rugby.
Yeah. Yeah.
Rugby. School team. You are simply practicing it. Right? Another team, club team, maybe.
Yeah.
Hey. Wonderful choice of
Yeah.
sports.
You should try this, right?
Yeah.
Oh,
Okay, see you later.
Very good. Very good.